Welcome to the third session in which we will focus on learning Bayesian networks from data and causal discovery. As an introduction, before I get into the slides, let me show you where we are going. So let's go back to Genie and give you this hello world brief demo so that the theory and whatever we talk about the algorithms does not bore you. You will see where we are going. Here's what we want to do. We want to be able to open a data file like this. A data file like this is known as a flat table. Flat table essentially has variables in columns and cases, records in rows. It's the starting point of every machine learning activity, a flat table. Even if it's not a flat table, then logically it is. The reason for that is that a table like this shows you the joint probability distribution over the variables. If these are variables, in the cases, you see how they co-occur. Very simple reason. So if we have a set like this, what we want to do is we want to learn a graph from it. Let me use the PC algorithm, which is the one that we are going to talk about the most. And here we are. Within a fraction of a second, I have learned a model. I can continue, obtain a model like this. Let me show it as a bar chart. Update immediately, do a layout, a better layout, because of course it's automatic. So the program didn't know too well how to do it right. I have a model. In fact, this is the model that I showed you just a little bit ago. The reason why I got the same model is that the data were generated from that graph. So I was able to retrieve that graph from the data. Now I can perform inference, as you see with this model. I can start observing things and seeing the variable that I wanted to predict. I can also look at things like thickness of arcs, etc. So I have obtained a graph that gives me insight into what I want, what the data is describing about the system in the world. And I can also give it a causal interpretation. So that's where we are going. Let me close it now and go back to the slides. Learning Bayesian networks and causal discovery. So far you have seen, we have reviewed the basic of statistics, some of the terms that you see a lot in Bayesian networks. In the previous session, you saw Bayesian networks, their theoretical foundations, and the family of Bayesian networks. Now, we are going to talk about learning them from data. The third session. Here is the overview of the session. I'm going to talk a lot about causality and probability. We need to understand what we are standing on. What is it that we are discovering? And for that, you need to develop the intuition of what causality is, how it is tied with probability. Then I'm going to spend a lot of time on the constraint-based learning, which is one of the approaches, one of the two major approaches to learning the structure. This approach is much easier to understand in terms of the relationship between causality and probability. Understand why the graphs we are learning can be given a causal interpretation. Bayesian learning is another approach. I'm going to outline it briefly to you. It's probably much easier to understand for computer scientists, but it doesn't show, it's not as clear as the first approach in terms of the link between causation and probability. I guess relationship between probability and causality is the important thing here. And then the principles behind learning the causal models. These are the main goals. Of course, I'll be using Genie, but you should not feel tied to using any software of your choice in your learning pursuits. What is it? What is learning theoretically? Theoretically, it is essentially starting with a set of variables and then measurements over this set of variables, simultaneous values, records. If you have that, the first goal of learning is to obtain insight into causal connections among the variables. So learn the structure of the graph. And you can use that structure, in addition to understanding, also for prediction of the effects of manipulation. And as a side effect, actually, maybe one could view it as the main goal, is learn the joint probability distribution over variables in this set X. With the joint distribution, you can build systems that you can embed into some kind of decision support systems and use it further to do useful things. Why are we interested in causality? The main reason, I think, is that causality allows us to predict the effects of manipulation. In fact, science is focusing on causality. Every scientific experiment has a goal, insight, and the main type of insight is causal insight. What causes what? Of course, we can ask more detailed questions like the precise type of functional interaction, dependence, etc. But the structure, causation, is the main goal. The second reason is that people, and that includes experts, all of us, tend to think in causal terms. So if you use your expert knowledge to build models or to refine models, you will be thinking in causal terms. And because of that, it's easier to have causal models because there is some level of compatibility. Of course, given the importance of causality, which allows us to predict the effects of intervention, manipulation, it's not surprising that people find causality so important. If I know what happens when I do something, that's an incredibly important knowledge, allows me to move around in the world. It's important and also not that easy. People gain that knowledge at the age of 5, 6, 7, I think. There have been studies of when children acquire causal knowledge. It's actually quite late in their development. Causality and probability, I mentioned that already in the first session. Typical statistics textbooks have this sentence, correlation does not mean causation. If at all, they use the word cause. That is changing. Even in 1990s, I've seen at least one textbook where there was a couple of pages devoted to causality. Not enough, not a lot, but a couple of pages. Because this word was dirty, as I told you in end of 19th century, when correlation was developed, people decided not to use the word cause. Some people even called it the relic of bygone age, the word cause. Because it was a dirty word, there were many substitute terms for it, somewhat confusing, but they were all causal terms, confounding factors, latent variable, intervening variable. It all talked about something about the causal structure without using the word cause. So the question is, what does correlation mean with respect to causality if it doesn't mean causation? In some branches of science, branches of statistics, the goal is to establish causation. For example, in all experiments, in experimental design, statistics is just a tool to help to interpret the results. There we need causality. So how are they related is important to know, and not knowing how they are related is really a handicap to a scientist. Causality and probability are closely related, and the relation is, it should be made clear and explicit. Typically, philosophers of science, it's a very practical branch of philosophy that looks at scientific method and makes statements whether scientific method makes sense or doesn't make sense, what the good and bad things about are. Philosophers of science typically believe that probabilistic dependence is a necessary condition for establishing causation. We don't even talk about causation when things are independent of one another. And when you have two variables like flu and fever, they are related, correlated, or dependent in general. Correlation is measure of linear dependence. I'll be often using correlation incorrectly, but just because this word has made its way to the common language, what I mean always is dependence, which is more general, probabilistic dependence. The two variables will be dependent probabilistically because flu may cause fever. A cause can cause an effect, but doesn't have to. So there may be people who have flu, but don't have fever. There may be people with fever who don't have flu, because fever may be coming about because of other diseases or other things. In any case, when there is a causal connection, you will see that in terms of dependence. You will see that among people who have flu, there's a higher incidence of fever than in the population. You will also notice that among people who have fever, there are more people who have flu than in the general population. You see dependence. They depend on one another. What I will do now is I'll take a break from the slides and go back to the software in order to show you a number of causal graphs and explain to you the consequences of Markov condition. Markov condition, I'll show it to you again on the slides, sounds somewhat theoretically. And if you do research that requires you to state it, to work with graphs, you may want to look at the original Markov condition and look at it strictly. What I will do in this demo that will last about 15-20 minutes, what I will do is I will show you the three important consequences of Markov condition, actually three important with respect to dependence, and then kind of a meta-level condition telling you about how to make things independent by conditioning. These are all consequences of Markov condition, 3 rules plus 1 meta rule. The first rule is that when you have a chain of influences, directed chain of influences like this one, flu causes fever, fever causes shivering. When I say causes, remember, I mean imperfect causation. Causation is rarely perfect. Flu can cause fever, but doesn't have to. Fever can be caused by other things also. So if I observe flu, I'm double-clicking on this to observe it, you see that the probability of fever changes. Yes, it impacts it. Knowledge of fever. When I have no flu, that probability also changes. So things on a chain, on a directed chain, are all dependent on one another. It's a consequence of Markov condition. Markov condition talks about conditioning on the parents. Then there's no conditioning, so they are dependent. They can be dependent. So a chain of connections leads to dependence, and it works in both directions. Fever causes shivering. If I observe shivering, then this will also lead to changes of probabilities of flu and fever. Marginal probabilities. What does it mean? You can explain it in many ways. If I notice somebody shivering, in my mind, that person has high probability of fever and high probability of flu. I'm talking in Bayesian terms, in terms of my beliefs. Anything on this chain is dependent. If I observe fever, both of these also change. So when you have a chain like this, direct influence, things become dependent. Things can be made independent by conditioning. You can break that chain by conditioning. So if I condition on fever, what does it mean? I'm essentially looking at people who have fever. My population everybody has fever. Please note that that has impacted probability of flu and probability of shivering. So because of the, the chain of connecting them. But now I have broken this chain by conditioning. I condition on fever, and flu and shivering are no longer dependent because conditioning here breaks it. Whether there is shivering or not, it does not impact flu. Does not impact fever, of course, because fever is fixed now. I have observed fever. But observing shivering makes no difference for the flu. The causes of fever make no difference to the effects of fever. Shivering depends directly only on fever and not on flu. So again, to sum up, a chain of connections, directed chain, makes things independent, everything on that chain, and you can break it by conditioning on anything in the middle that separates the rest. That is something that has been known for forever, and I suspect that it's quite intuitive to you, this consequence of Markov condition. Here is another example. Ice cream consumption and drowning. It turns out that they are very correlated. If you learn that there was a lot of ice cream consumed in Grimstad, you can predict that there were more drownings than normally. If you learn that there was very little ice cream consumed, there will be fewer drownings also. If you learn that several people drowned on a given day, you can safely predict that there was more ice cream consumed. What is happening here? Here is a graph that is quite likely the case. There is a common cause, outside temperature. On a warm day, people tend to eat a lot of ice cream to cool down. And also, on a warm day, I'm double-clicking to show you the change. People are also swimming outdoors more, and some of those people are drowning. A common cause can result in dependence, probabilistic dependence. Now, with this unobserved, look what happens. I observed a lot of ice cream consumed. This conducts dependence. The common cause works as a conductor here. Conditioning on common cause breaks that connection. If I know it's warm, whether a lot of ice cream was consumed or not, doesn't matter. It does not impact drowning and swimming outdoors. But if I don't observe it, then there is a dependence, which through a chain first, and then through a common cause gets here. So common causes result in effects. Again, something like this has been known for a long, long time. The intuition existed in science and probably common sense also. Here I'm just fooling around a little bit. I don't believe this is the case, but I just wanted to fool around with the idea of this statement that scientists are saying these days, that moderate alcohol consumption, especially wine, red wine, impacts heart disease. So if you drink in moderation, you have a lower probability of heart disease. By the way, all the numbers in this model are mine, from my head, so you don't need to trust the numbers. But the qualitative dependencies, the correlations, dependencies, they are real. We know about them. If you abstain from alcohol consumption, the probability of heart disease goes up. I believe that in this case, there may be a causal connection. There have been some experiments showing that alcohol, especially red wine, does some dissolution of, dissolves the fats in the blood veins. But again, the evidence is not terribly strong. And you should not, if you believe that, you should not drink too much, because drinking too much increases the probabilities of other disorders, liver disorders, all kinds of cancers, etc. Here is what I have invented here for this thing. I don't believe this is true, by the way, so don't believe me here. But that common cause would explain why there is a correlation between wine consumption and heart disease. What's the story I want to tell by this graph? Life enjoyment essentially means that you are relaxed. You don't work in the evening, do you? Of course, that's a joke, because most scientists, most professionals often think about other things about their work in the evening. But suppose you can relax, you enjoy life. What do you do when you get home at 5 o'clock? People don't work longer who enjoy life, 5 or 6 o'clock. Well, they start cooking dinner with their spouse, significant other. They pour some wine while they chat, tell jokes, and what happened at work, right? So the probability of alcohol consumption goes up when you enjoy life. When you don't, of course, it goes down. At the same time, when you enjoy life, when you are relaxed, you don't worry too much, the probability of heart disease goes down. We know it. Stress is a risk factor for many diseases. When you are more tense, probability of heart disease may go up. And now, because of this common cause, we observe the dependence that I showed you on the left. So this graph, which I don't believe is the true graph, I do believe there is actually a connection between wine consumption and heart disease. And this graph explains the correlation. You see the difficulty when you observe correlation or dependence in the world, you don't know what it is, whether it goes like this or the other way, or whether there is a common cause. This is where this statement, correlation does not mean causation, comes from. There is a correlation that I mentioned in the first session. Top surgeons actually don't have the best statistics. In US, you can check the statistics of your surgeon before undergoing an operation. It turns out that the best surgeons have a higher death rate than average surgeons. What is the explanation of that? Here is a possible explanation. There is a common cause, the difficulty of the case. When the case is difficult, it goes to top surgeons, people who have experience. And at the same time, difficult cases have a higher risk of death. Easy cases go to less experienced surgeons, and also have a higher probability of success, lower probability of death. That common cause accounts for a positive correlation between positive dependence between being very good and death. This link has negative influence. If we look at difficult cases only, top surgeons have twice as low death rate as average surgeons. But then I want to mention again that the numbers are mine, I invented them. But the existence of this dependence is real. Easy cases, top surgeons have lower death rate than average surgeons. So it's still a very good idea to go to top surgeons, even though the relation between the death and the being very good is positive. Top surgeons have a higher death rate. Again, this is just playing on this idea of common causes and chains. Now the third rule. So I told you about the two rules: a chain, common causes, and the third rule is difficult. It's so difficult that people formalized it in statistics only in 1970s. It was a German statistician, Nanny Vermuth, who formalized it and described it. She's a German statistician. Brilliant discovery. Once you see it, you realize that you've been using it all your life. And interesting that statistics models it correctly. What is that rule? If you condition on the causes may be independent on one another. In this case, a simple example is barometric pressure is independent of my my little brother, who likes to fool around with the barometer and blow in it to make the barometer reading high. Blows in the pipe, the mercury level goes up, etc. So as I change this, you see that there is no common cause, there is no connection between the two, so they are independent. Of course, the manipulation impacts the reading. The same with barometric pressure. If the pressure is high, the barometer will show it by the way it's constructed. Low, it will also show it. No dependence between the two. However, when I see the barometer reading to be high, being high, when I see it's high, of course, both of these go up, dependence, right? Now, the causes become dependent, conditional on the common effect. When I hear on the radio that the barometer pressure is high, my thoughts about my brother joking with the barometer goes down. If I hear that the pressure is low, oops, it was probably my brother, right? The probability goes up. The same if I see in his eyes that he has this mischievous look, I believe that the barometer pressure probably is not that high, right? So you see that deep conditional dependence. Difficult to think, formalized, and probability theory does it correctly. Here's a more complex example. 4 different causes of marital problems. Drinking, addiction, unfaithfulness. If you drink, you will have problems. If you are addicted, 2. Unfaithful, sure. 2, dependent emotionally on your parents, the same. Please note that they are independent in this model. There are no common causes, no connections, and as I change one, the others are staying. Now I hear that there is no John here, so I can say John. John has marital problems, right? Please note what happened. All of the causes became more likely. When we hear that John has marital problems, we think, okay, what was it, right? Causes of things are more interesting than things themselves. That's a citation from a Roman thinker. I forgot which one it was, Cicero or somebody. Well, something must have caused those problems. They don't just pop up out of nowhere. So you see that the causes become more likely. What was it? Suppose we learn that John has been unfaithful to his girlfriends before marriage, to his wife after marriage. We learn about his unfaithfulness. Look, when I observe it, the probability of the other causes of marital problems go down, right? Again, conditional dependence. When you condition on common effect, the causes become dependent. Correctly modeled in statistics. Interesting observation. It's also a consequence of Markov condition. In what sense? Markov condition tells you about independencies when you condition on immediate parents. It does not tell you anything about dependencies of conditional dependencies, but it doesn't make any statements about these things being independent. So if they are not independent, they may be dependent. Here is an interesting thing for you because many of you work with data analysis. It is a fact that there is a strong correlation between heart problems and lung problems in intensive care units. So if I observe that a patient has heart problems, the probability of lung problems go down, and vice versa. They are high a priori because people are in the intensive care units. The explanation of this is the following. These two are very important causes of landing in an intensive care unit. If you have heart problems, they immediately put you there because if your heart stops, you die. The same with lung problems. If you stop breathing, you die. So if you have difficulties with breathing, you get to an intensive care unit. The two may be independent of one another. Maybe they are not, but in this model, they are independent. If you collect your data in an intensive care unit, you'll of course observe that both of these are likely, probably more likely than in the general population. But you will observe in your data set that they are very dependent. So you will see spurious dependence that is caused by the way that you collected your data. You collected your data in an intensive care unit. That's what the conditioning is. And that has resulted in spurious dependencies. So a very important advice for any type of data analysis, always reflect on how the data were collected. Were there any conditioning things that could introduce dependencies? That's it, really. This is just a more complex problem where I can explain the Markov condition. Well, we talked about dependencies. If I change lethargy, if I observe lethargy, which things are going to be dependent? Well, jaundice, a common cause. Bilirubin, direct connection. Liver cancer, link, chain. Hepatitis B, a chain. Antibody test, common cause. So everything is going to be dependent if I observe it, right? If I observe, and liver cancer is going to be dependent on what? Just these things, because there are chains here. There's nothing else that connects liver cancer to those. But please know that liver cancer is independent on hepatitis B. If I observe bilirubin level to be increased, of course, everything is impacted, everything is connected to it. But now, if I observe lethargy, tells me nothing about the jaundice, because jaundice is caused only by bilirubin level. Lethargy or not doesn't change anything. When I observe lethargy, nothing changes here because bilirubin level is making them independent, screening them. Liver cancer, though, is going to be dependent on hepatitis B because a common effect was observed. And through this common cause, this is also impacted. By the way, this common observation can be common descendant also. If jaundice is observed, it's a common descendant of liver cancer and hepatitis, you see that dependence also. So that is all in terms of the consequences of Markov condition. You can read from the graph which things are going to be dependent in the data, just based on the graph. The graph will tell you things that are dependent. Of course, you can also read from the graph which things are going to be independent. That's just missing arrows, right? Liver cancer and lethargy can be independent. Normally they are dependent, right? But if I condition on this, I'm breaking that chain. Lethargy and liver cancer are going to be independent now. Missing arrow. No, they can be made independent. What else? Can I make jaundice and lethargy independent? Sure, I can. By observing bilirubin, I'm breaking that common cause. Now they are independent. So you can read from the graph, here's a missing arrow, antibody test and jaundice. There are several ways of making them independent. Hepatitis B will break that common cause. So now antibody tests will change things, jaundice will change things, but they will not be dependent anymore. You can read it from the graph. Missing arrows and from the connections you can read it. So now, once we have that, once we have this understanding of the causation and dependence, please note that when I have data generated by this graph, what does it mean generated by this graph? No, well, there is something in the world, some system that can be modeled like this, described by that. In that real world system, there are causal connections. I'm just measuring that system. I'm collecting data. if that system generates the data and you observe in your data that some things are independent, you know they are not connected. Yes, that's what learning the structure is going to be about. We are going to look at the data. The data are going to show us dependencies. And from that, we are going to infer which graph we are dealing with. The next few slides I'm going to run very quickly because we have already talked about the consequences of Markov condition. Here's just another graph. It's more interesting to do it live. That's why I did it live rather than in this graph. This graph demonstrates an important idea that all knowledge, all models in science are subjective. This graph is a model, scientific model, telling me how things are interacted with one another. And the subjectivity comes from me choosing which variables to include. When you are a data scientist, you don't make that choice yourself. Somebody else collected the data, maybe. That person has made the choice what things to include in your model. Another thing that that person did is choosing the level of granularity. For example, flat tire, yes, no, instead of, for example, tire pressure, continuous variable. That person made that choice collecting the data. And that was a subjective choice, really. That subjective is science. Another thing is, of course, the choice of variables that I mentioned. Everything is connected with everything in the world. You know it. In this graph, I made a joke here. You see, accident caused by a flat tire can cause car damage and injury. Injury can be also caused by a knife and a gun. I decided to leave out a gun and put a knife in my model. That was my decision. So you see, the graphs are to a large degree subjective. Even though I'm a scientist, I'm using my mind to create those graphs, to do investigations. In that sense, it's subjective. So this objectivity of science, science is objective in other aspects, but in terms of these graphs, it's not terribly objective. Causal connections result in correlations or dependencies. So glass and flat tire are connected. There will be dependence. Those roads that have a lot of broken glass will have more flat tire. Places where people got flat tires will tend to have more glass spread than other places. Noise and glass are going to be related too through this chain. Noise and bumpy feeling are going to be related too because of there's a common cause, a flat tire. These are consequences of Markov condition. The Markov condition, phrased as a causal Markov condition, the only difference is here that the graph is causal. It's not the directed cyclic graph. It's a causal graph. A variable is independent of its non-descendants given its immediate predecessors. That's really a somewhat formally stated condition. There is something very closely related to that, the concept of Markov blanket. Let me get a more complex model, maybe the Hepar model that is probably more complex than that, complex enough. Let's take a variable that is fairly densely connected. Let's take this variable, presence of hepatitis B surface antigen in blood. Let me look at connections of this variable, and let's show the Markov blanket. Markov blanket of this variable contains three variables. Chronic hepatitis, let me show them, highlight them. Here they are. This variable, the Markov blanket of that variable is these three variables. Immediate predecessors, they will screen off everything that is up the stream from there. Descendants will screen from the further descendants. And this was actually not a very good choice. There is, we also need descendants of, parents of those descendants. Let me do it Let's take, does it have parents? Yeah, it has parents. Cancer is a good variable. Let me show the connections of this. Markov blanket will have, no, too few. Let's I should be better prepared for this. Maybe this is a good variable. Let's show the connections here. Markov blanket will, look at this. The Markov blanket of this variable has many, many variables. Let's highlight them. This variable. In order to make this variable independent of everything else, you need this variable in here. Why? Well, you need parents. These parents, like history of transfusion, will make it independent of their ancestors, right? So you need all the parents. You need all the children. Let me see. Unfortunately, we only have one layer. We don't have children of the children here. So not a terribly good choice. Oh no, we do. Total bilirubin is a child of chronic hepatitis. In order to screen it from jaundice, we condition on the child of hepatitis, so the children. And then you need the parents of those children. So if you have a child here, you need the parents. If you don't condition on the parents, this one, what will happen is because of the conditioning on this, it's conditioned on, this will be dependent through the common cause. So in order to separate it from chronic hepatitis, you need to condition on this one also, the parents of the children. So parents, children, and the parents of those children. As you see in case of chronic hepatitis, there are many variables that you need to screen chronic hepatitis from everything else. So that was the practical demonstration of the theory. This is an assumption, an axiom, but this axiom has very good empirical foundation. So it has been shown, found, observed that when the graph is causal, then this condition holds. It's an axiom, and people, of course, philosophers of science mainly, were trying to undermine this, saying, look, here is a counterexample. This thing doesn't hold. Luckily, to me, most of the responses to those counterexamples were convincing. So I'm myself convinced that this assumption is quite a sound assumption about the world, at least in the macro world. We know for sure now that this assumption doesn't hold in the quantum world. When you have particles, quantum world, quantum theory, Markov condition doesn't hold. But there are many more weird things in quantum, at the quantum level than this. So it's not terribly surprising to me that Markov condition doesn't hold there. An assumption. Consequences, I already explained to you. Chains will make things dependent. Common causes will make things dependent. Conditioning on common effects will make things dependent. Here is the summary of those three. I'm rushing because you've seen that already. And the next thing is conditional independence. I talked about this in this demo of the models, the examples. If you condition on flat tire, you break all the chains coming from glass, thorns, and nails down. So it's almost as if these arcs were dimmed, inactive. You also break the connections between the descendants of that variable. Bumpy feeling and noise are going to be no longer dependent. Of course, you make the ancestors dependent, but that was one of the consequences of that condition. A side step from discovery, just a side step to show you how close this is to to science. There is a theorem by Spiritus, Glimmer, and Shyness. All three are philosophers, saying that if there is an external intervention in a causal graph, you can predict the effects of that intervention by just modifying the distribution over the variable that you manipulate. If that intervention is perfect, which is the easiest to understand, you kind of fix it from the outside, then the causes, the incoming arcs, are irrelevant. You can just remove them. Here is nothing else needs to be modified to make predictions. Here is a somewhat not terribly tasteful joke on that, demonstrating the idea. The samurai is cutting his belly, killing himself, and discovering that he had a cancer, intestine cancer. Cancer, diabetes, AIDS, COVID are all irrelevant to the variable he is alive. He's killing himself. He's performing a perfect manipulation. All kinds of terrible diseases that he might have had or might have developed in the future are completely irrelevant through intervention. If I take a knife and cut my tire flat, I fix it. It's flat. I make things independent, and I can actually predict what will happen to the other variables, but it will be irrelevant how much glass, thorns, and nails were there. If we have correlation or dependence in life, let's say smoking and lung cancer, if we don't randomize, if we don't perform an experiment, we have this classical thing: correlation does not mean causation. We can have three possibilities, at least: cause going in one direction, cause going in the other direction, or genetic factors causing both. It makes sense because we know that there are genetic factors in developing all kinds of cancers, and there may be genetic factors causing people to smoke. Some people are born with preference for sweet things or sour things. The same with smoking. Some people like the feeling of smoke in their lungs. Some people dislike it. In that sense, genetic factors may cause smoking. So the dependence may be through a common cause. What is experimentation about? Experimentation is about investigating why things are dependent. Dependence is really the beginning, the thing that makes us study something. Anything is possible here. Correlation does not mean causation in this case. We can have a common cause. We can have smoking causing cancer, or we can have cancer causing smoking. Any of the three is possible. And which one is it? Experimentation, which is what we do, we randomize. That means for every individual in our study, let's say we have 2,000 individuals for our study of smoking, influence of smoking on lung cancer. By means of a coin, we decide for every individual whether that person will be smoker or non-smoker. From today on, whether you liked smoking or you didn't like smoking, it doesn't matter. The coin decides for you that you are a smoker or non-smoker. Perfect intervention makes genetic factors and lung cancer causing smoking irrelevant, completely irrelevant. If at the end of the experiment you discover that smoking and lung cancer are dependent, so there are more cancers among the smokers than among non-smokers, you know that this could have been only through this connection, in this direction. This is the way experiments work. And the author of these experiments, Ronald Fisher, a British statistician, I'll mention him on the next slide, never believed that there is a connection here this way. He was always joking about this, and it is true that never an experiment was able to show that. Experiments with animals never led to showing that smoking can cause cancer. I suspect that animals essentially live too short to develop lung cancer. It's a type of cancer that takes longer to develop. We cannot experiment in a domain like this. So the question is, what can we do? We can observe. Two jokes about observation. Ronald Fisher, who always doubted that smoking can cause cancer, at least he was saying, nobody has ever shown it, and anything is possible. Here's another joke, actually a real situation, vice presidential debate in 1992 between Al Gore and Dan Quayle. Dan Quayle had always a bad press. He was laughed at apparently for saying stupid things. I think they treated him also unfairly. They were often inventing his statements. In this case, it was a true statement. He was saying essentially that my running mate, George Bush Sr., caused the Cold War to stop. Fall of the Berlin Wall, the end of the Cold War, that was the work of George Bush Sr. And Al Gore, who was very quick with language, said the following: it's essentially a common cause. It's like a rooster causing a daybreak. It's common cause, right? Or correlation and not causation. Experimentation is not always possible, and we can do a lot by observing. In both experimentation and observation, we need assumptions. Assumptions in case of causal discovery from data need to be stronger because it's a less powerful tool. The new methods are squeezing the data to the limits, really to the limits. Well, there may be other limits, but we don't know. The constraint search-based and Bayesian search learning are the two approaches. As I mentioned, I will spend more time on constraint search-based learning than I will on Bayesian search, just because the connection between causality and the graphs and the algorithms is much clearer, and dependence. The first approach, constraint search-based learning, was developed by Peter Spirtes, Clark Glimmerk, and Richard Shines. They are all philosophers at Carnegie Mellon Philosophy Department. Another person who did work, in fact, they were in parallel, but there were a lot of contributions of Yuda Pearl with his student Tom Verma. Essentially very similar approach. Some of the things were done earlier by Spirtes, Glimmer, and Shines. Some of the things were done for the first time by Pearl, I believe. In any case, these are the two groups. I'm going to talk about framing the formalization by Spirtes, Glimmer, and Shines. The other approach was started by Greg Cooper and Eddie Herskovits, his student. They showed a completely different way of doing this. I will cover both, but I will spend more time on the constraint constraint-based learning, and we'll talk more about that.